Okay, so I am going to talk to you about the nuclear chemistry, and I will start with the symbols on alpha, beta, gamma, and particularly also these nuclear symbols. In addition, today I'm going to more focus on getting down to the math on the half-life, and that seems to be the very important concept. We deal with this concept from the kinetic equation, first order equation, and the radioactive decay is always a first order reaction, most of the cases. So that therefore we just need to focus on the first order kinetics and the meaning of the half-life once more. But let's get started with something that is unique to the nuclear chemistry. You heard about alpha, beta, gamma ray. This is just a languages that is happen to be named by somebody who's doing this experiment. Rutherford is a Nobel Prize winner who really revealed the identity about the nucleus or atomic structures. And this is his famous experiment. When he has this experiment in the vacuum tube, and he has this source that it emits the either alpha, beta, gamma, and he put this source into the essentially across this electric field. So there is a plus potential and the minus potential is being charged, and he find out as far as the alpha particle he call it just fall onto the plus side, okay, and the beta particle goes to this other side. So, and the gamma doesn't care, it just go to straight through, just like you remember the diamagnetic just going through the magnetic field without having interaction. That's just like that. And at that time they did not have an idea about even the clear idea about the electrons and all the concepts. So he just named it as, okay, alpha, beta, gamma. First one alpha, second one beta, third one gamma. And then later he find out the alpha particle was a helium, which is atomic number 2 protons with the atomic mass of 4 and has a plus 2 charges. So we can think about alpha particle as a one, the positively charged one. At the same time, in the nuclear reaction, it's also handy for you. They easily lost, so that you can just think about number of protons and the number of neutron and proton combined. So that's an alpha particle that is probably mysterious when you first see that. It just happened to be his first particle system that's being attracted to the negative particle. He just say, okay, this is the first one, so let me call alpha. And he said he did the second experiment, which is a beta, and the beta is something that these days nobody would not call this a beta, because it's just an electron. An electron has almost no mass, so he just put the zero mass, and the charges, it looks like having opposite sign of the proton, so it's a -1 is what they use. And the gamma is just nothing but, remember the H nu, electromagnetic wave? This is just a light. Light go through, and then they just do not have any charges. So it is just an energy, which is a photon. So this is a photons particle, and then they have no, they are not bending, they are being bent by the electric field. Okay, and now this is a notation that you want to know, and we've been using this notation or this particle name, which is a proton, neutron, electron, and the symbol that most people use here, and I don't know, the proton. You can do this or you can do that. I think that this is all acceptable. But now you have to forgive those who has come up with this alpha and the beta particle, and the beta is typically meaning that you have an electron. Okay, so that's, although they are saying beta, that's an electron. Alpha, just the first significant one. This is really the notation they're using a helium. And as far as I know, it's like the people would not use this notation for this is the rarely being used. Yeah, I mean we can use that beta with a negative to give a contrast to the one that with a positron. So this is a positron is the one with the plus charges, which is a sort of the opposite of the beta, right? If you look at that, the people call it as antimatter because when you see the beta, which is an electron and positron combined, you ended up having, if you having added up together, they're fused together, there's nothing, right? No mass, no. So it's like a 0 and 0. But what's going to happen is, so there will be some kind of energy will be emitted, and that's the nuclear reaction. So this gives you another interesting snapshot on this. This is the same languages. When you say emission, means a reaction happens and something is happen at the end. I mean that's what the name suggests. When you're looking at capture, means before the reaction happened, something gotta be reacted with what you have already. Right? So then you can follow this as a beta. Beta means electron. So I would people probably prefer to write this, and that's good. And the positron means they use +1 and almost no mass. So that's the one they are using it. Electron capture is the one that some of them is actually can have an electron, so you are really losing, decreasing the number of proton. The proton can react with the electron to have a form of a neutron, so that's the things that you can see. I also here I provided the 4 examples, and this is an example, actually the answer key for your discussion problem number 1. If you have looked at it, you can see how this problem is being solved. And then I think that I like to use this highlighter that I have and to see what is an information that you are seeing here. To me, the most important information is this. And this information is actually, in a way, redundant. You see this plutonium? And this is an atomic number or number of protons. Okay, so let me put a little light here. And 92, so where is the 92? This is very fine print. So yeah, this is a plutonium. Is it 94? Yeah, it's a 94. I'm sorry, it's a 94? Yeah, it is 94. Yes, a 94 plutonium. I think most of you know. When you write helium, that means we already know uranium means 92. So it's when people write this atomic symbol, it's pretty much determined what you guys see. And uranium was 92. Let me see the 92 here. Yeah, that's a uranium. See, the plutonium is 94, uranium is 92. So this is the same thing that you guys see. So that's one simple thing that you can take advantage of. But I like to write a little notation. They call it Z, but I just like to write P. Okay. And what's this number? That's the total number of neutron plus proton combined. So if you can see from here, you guys can find out what's the number of neutrons in there, right? And so that's here. So you just let me do this 12 proton means magnesium, right? And this is just a positron, and that's a 13 proton means aluminum. So you can find this based on this information from the periodic table. You can kind of follow this notation. So essentially, that's what this is give it to you. And then also the nuclear reaction wants to know Okay, this is what you call alpha particle. So this is an alpha particle emission. This is a beta ray emission. This is a so this is a positron emission, and this is a one actually electron react. So this one is an electron capture. So the way that it works out is the number of proton, right? 94 is you have a positron, the alpha particle emitted. So therefore, you need 92, and then you look up the periodic table. That's the uranium. So that's why you're going to write 92. And the second step is okay. So the N. How much is an N, which is a 292. Well, you can just say N plus P. So let's just say 292. Okay, so it's just a 292. N plus P is a 242. And then you got 4. So how many do you need here? It's a 238, right? So you're going to write 238. That's how you ended up writing this one at here. Okay, so almost finding the 92 first, and you can look at the periodic table, writing the uranium symbol, and then you can finish the rest of these notations. So that's here. Let me try one more example, and then this is here, right? You can see that. Okay, so let me start with the number of protons, and okay, in the beginning is a 14, and then this is a positron because it's like an electron with a different plus charges. So and then so you have a 1 proton, so you need 13, and you look up the periodic table. That's an aluminum 13. So this is how far you can go from the first section, and the second step is now looking at 26, 0. So therefore it is a 26. So you're going to write 26 on top. That is a number of neutrons and proton combined, and I think that you're done, right? So this is what you write, and you can say that's a positron emission. Okay, so that's an alpha emission, and this is a beta emission. This is a positron emission. They can write in various terms. This is I guess electron capture. I think that they don't say the beta ray capture. Just say the electron capture is much more common to say. Okay, so today I am going to more focus on talking to you. Yeah, but this is the periodic table is always candy for you to remember what is my atomic number. I mean, this is a topic that we just talked about it. Aluminum is 13, right? And silicon is 14. So you guys can all find out. So this periodic table is very important. Okay, so let me do the half-life and radioisotope decay, and this is a topic, key topic for today's discussion. Half-life has a symbol of that. Okay, so this is a symbol that you'll see the half T with a subscript with half in there. That's the one. And then the definition half-life. This is the only thing that I remember the most, which is a half-life is time to take your concentration of your concentration of A, which is your reactant, to be the remaining only the half for what was original. So this is an initial, and then this is at certain time, but at the time T is T half-life. Okay, you'll reach the essential 50% of the whole thing. So here's the graph that I was able to find out from actually one of the slide, and this one is trying to say, okay, this is 100%. So I am going to say this is your initial concentration is 100%, and so then you look for the time. This is your situation when your concentration is half of original concentration, which is 50%. Right? So then this is a time. If you look at that, that's the graph, and that will be the half-life. Interestingly, they show you that how long does it take for the half-life. So this means that this is a one half-life, this is a second half-life, this is a third half-life, and so on. So in general, what this radioactive decay means, you always has an original concentration, and this one drops. As time goes on, you start to lose this one into the products. And in our class before, we wrote this way, right? A goes to product, and this is a first order. How do I write? This is a first order reaction. And do you remember? So that's the same thing as for us to write. And there are equations that people remember to use. And then the first equation is, this is an equation I write it way. So this is trying to show you that this is an exponential decay. So this line shown up here is an exponential decay from the original concentration with an exponential decay function as time goes on. And then with the decay constant k is your rate constant k for the first order decay reaction, right? And also another way people write it is, okay, this is a naught of a naught. A over a naught is minus kt, or sometimes people write it, you kind of flip this as a naught over a, not a over a naught, and then in this case it became plus t. Okay, so plus kt. And so there are three different versions. This version is pretty much simple to understand what this a versus the time, and there's this exponential decay. You can kind of put this one into the natural log term, but depending on which one is on the numerator and the denominator, it can have a different sign. And do you have to remember this equation? The answer is no. You don't have to. Okay, so let's have a look at this. So if you look at here, this is actually from the chemical kinetics. And do you see this equation here? That's the equation that is for the first order equation. If you look at that, it's essentially the same equation. And also the half-life shown up here is for the first order equation. They didn't show the half-life for the second order equation. First order equation in your exam reference sheet is shown in this form, shown in that form. But personally, I don't like this the way that it's written here. This is much more easier. It's much easier for you to understand in terms of the ratio. Okay, so the ratio. So this one is smaller than that. So this term is always a negative. So to match the sign, it is a negative here. Well, you can, if you prefer to positives, and then this is the way the ratio in the natural log term is on kt. So you should remember this term, and I also like the graphical way, so people like this way as well. So it's up to you guys to decide, and we're going to solve the problem that is related to. So once again, look for the original concentration when it comes to the half, and is how long it takes. That is on half-life. Okay, and because it showed the exponential decay, this concentration is one more time minus kt, and then something happened. Okay, and the half-life is what is being used a lot, and the half-life is what you see, and it is actually related to natural log 2 divided by k. So half-life is a way to measure the reaction constant K, and they are related to this way. Okay, this equation. And this equation, half-life is natural log 2 divided by K, can be found from the reference sheet as well. Okay, and here's an example that I also find it from your slide in the class. And then the radon. When you buy the new house, actually sometimes you need to do the radon test. Okay, and the radon test is radioactive, and you can see that they actually show this graph, right? Okay, so this is the original. So I only need to look at the time that is go to the halfway, which is 500,000, right? So then that's the time, and this is the one. So that will be the essentially T half-life, because your A concentration is half of your original concentration, right? At time is T half. So always remember that, and then you can solve the many problems. Has a good starting point here. So the answer here is on 1 minute. I think that's it for now for this crash course.